I know that while we were having our class on Friday, my wife snuck into my office and decorated it. That's what love is right there. That's it. Picture form. That was pretty neat. All in all, pretty good birthday. I went home at like 1 o'clock and just drank lots of beer and it was good. All right, so today is basically we're gonna spend it looking at NMR spectra and solving them. And our theme song today is "Jigsaw Puzzle" by the Stones. So this is very much a puzzle, and so we're gonna have lots of little pieces of information that we're able to extract from our NMR spectra. And ultimately, we have to put the full picture together. It can be a little bit challenging, and certainly what we can do, and what you'll find is as we solve problems, there's going to be themes that drop off, right? We're going to see similar motifs that always indicate the same thing, and so with practice, we should be able to solve these pretty well. I think I was looking at last year's, or at least the practice exams from the other professor I've been posting, and so those exams are typically, about half of them are solve spectra. So this is going to be a relatively big chunk of exam 3. So we're going to be doing that. I'll give you some practice problems. I'll get those posted today. And we're also going to be spending 2 weeks in lab. So the next 2 weeks in lab, we're going to be basically solving spectra. So again, it's highly emphasized because it's something that you don't just know from looking at it. You have to really practice at these. All right, so hopefully everyone's got the printout that I asked you to print out. And so quickly, just to go over how we're going to be interpreting NMR spectra. One thing, so rule number 1, or I guess step number 1, we haven't talked about really, but what there is there's this magic formula, which is listed right here, and I will always supply to you. And so this formula, basically, you insert the number of atoms, and magically, what pops out is always going to be a whole number. And so that whole number indicates how many rings or double bonds there are in your structure. And so that's just an extra piece of information we can use to ultimately get to the true nature of our compound. All right, so we talked about most of these things last week, but we'll see that there's different sets of signals based on how many equivalent hydrogens there are, and so we need to be able to locate the different signals. Each of those signals can be integrated, which tells us how many hydrogens are basically represented by each of those signals. So then we look at chemical shift data, and so chemical shift data tells us basically how de-shielded those protons are, right? So that gives us clues as to what's nearby. We talked about how an electronegative atom nearby can withdraw electron density, right? And so it can de-shield a proton, and so we end up seeing it shifted downfield in that case. So those are some clues. We also talked about the anisotropic effect, which has a little bit of a role. And then finally, splitting. And so what splitting does is it gives us information about what's next door to our protons in question. And so if we see a triplet, we learned that the N+1 rule would tell us that there are 2 neighboring protons, right? So that again is just extra information that allows us to put some pieces together. All right, so I'm really frustrated with technology today. I'm going to have to use PowerPoint, which is like my least favorite thing in the world. Okay, all right, so we will be annotating as we go. So what we could have is we have some mystery compound. We know that mystery compound's formula, and you'll always be given the mystery compound's formula. So you need to know the formula so that you can plug all those numbers into our index of hydrogen deficiency. And that tells us, again, how many pi bonds or rings we have in our structure. So if we start out with that part, we're going to have 2 times the number of carbons we've got, which is 4, plus no nitrogens, give myself a paper cut, minus 8 hydrogens, minus, what's X? Halogens. We've got no halogens, plus 2, and so we've got 4 times 2 is 8, minus 8 is 0, plus 2 is 2 divided by 2 equals 1. And so what this is by doing this formula, what we figured out is that in our structure, we must have 1 ring or pi bond. And so in cases where you have a number greater than 1, it doesn't always have to be 2 pi bonds or 2 rings. It could be a mix. So if you had a number of 2, that could be 1 pi bond and 1 ring, or it could mean 2 rings, Or it could mean 2 pi bonds. So any possible combinations of rings and pi bonds must add up to that number right there. All right, so how many signals do we see in this structure? All right, so I see one signal here. Now that signal, we don't just see one peak, but what artifact, or what accounts for the fact that we see multiple peaks for one structure here? It's splitting, right? So we have one peak here, and then we have another peak here and another peak here. And so what this red line here is, this is done after the fact. So we obtain our spectrum, and so it comes into the computer, it just sees the black peaks. And so then we ask our computer to go ahead and integrate these peaks. And so the way that we tell the area of our compounds, or at least of our peaks, I mean, is going to be the distance between here and here represents the area. And so between, say, peak A and peak B, which one has more area? It's peak B, right? Because we can see that the red line basically is taller. So it's the difference of this gap versus this gap. And so if we can see the raw data, what we would have in this case, this would be about 2, this would be about 3, and so you can see that the integration for peak C is very similar, and so that gives us a 3 as well. All right, so how many total protons is this? What is the sum of these 3 numbers? 8, and so does that match up with our molecular formula? Yeah, we have 8 protons in our molecular formula. So these integrations make sense. They always need to basically equal our molecular formula. All right, so our integrations we can write down as 2. Peak B we know is 3. And then peak C we also know is 3. All right, so let's talk about some chemical shift information. Yeah?
How do you know that it's 2, 3, 3?
So basically, do you see how this one kind of adds up to roughly 2/3 of this peak over here, or at least the integration here of the red? You'll have these numbers on a problem. They're just not showing up really well on this. And so there's these practice examples I found that it doesn't come with the numbers. So that's why I'm actually giving you 2 and 3 and 3 here. But basically, you know, back in the old days before the computers that we had to manipulate all this information, what you do, you would literally just measure the distance from the bottom to the top of the red line, and then measure it over here, and so you're going to end up with something in millimeters, but ultimately you just want to convert that all to whole numbers, like 2, 3, and 3. Yeah. Okay, so we've got integrations for all of our peaks. So next we'll look at some chemical shift information. So which peak is furthest downfield? Meaning this peak is the most de-shielded, A, B, or C? It's A, right? And so anytime, and this is going to be something that comes up a lot, anytime we have a peak that is right around 4.0, what that's indicating is we've got protons that are next to an oxygen, nitrogen, or halogen. So our chemical shift, which is right around 4.0, indicates that we have protons that are next to oxygen, nitrogen, or halogen. In this case, what must it be? It must be oxygen, right? Because we don't have any nitrogens and we don't have any halogens. So what we've learned is based off of this chemical shift, we've got protons next to an oxygen, and so that oxygen is withdrawing electron density. And so ultimately we have peak A, which is very de-shielded. When we look at that peak, what kind of splitting do we see? So I know it doesn't show up very well, but what we've got is ultimately we've got 4 peaks here. And so what do we call the splitting when we see 4 peaks? Yep, that's a quartet. And so let's think if we can put this information together. So if it's a quartet, it indicates that these protons are next to how many hydrogens that are neighboring it? 3, right? Because we know the n+1 rule. What very common group in organic chemistry has 3 protons? Just a methyl group, a CH3, right? So what this indicates is that we most likely have a CH2 next to a CH3, right? All right, so we know that our protons in question here, there's 2 of them, so that indicates CH2. We know that it's going to be next to an oxygen, and we know it's also most likely next to a CH3 because we see it split into a quartet. So when you're doing these problems, basically what you're going to want to do is you're going to take as much information as you can and put together a fragment. And then you'll take more information and you'll put together another fragment. And at the end, hopefully we've got enough fragments that we can just put the real structure together. So for this fragment, what we can say is we have a CH2 next to an oxygen and also next to a methyl group. So this is going to be peak A. We know that it's next to an oxygen based off of the chemical shift, and we know it's next to a methyl because we see that it's split into a quartet. So we're able to come up with this, this little fragment. All right, so also in this fragment, we've got a methyl group. Now, if we had a methyl group, what would the splitting for this signal be expected to be? How many neighboring protons does it have? 2. And so following the n+1 rule, what would the splitting be expected to be? 3. So that's a triplet, right? Do we have another peak somewhere that is a triplet?
Yeah.
Yeah, we do. And so what that tells us is that most likely what we've got is these protons right here are going to be signal C. All right, so let's see. Our chemical shift for signal C is down around 1, which indicates that it's just going to be a regular alkane. And so furthermore, the coupling is a triplet. And so our triplet indicates that we've got a CH3 next to a CH2. And so in fact, that's exactly what we've got right here. We've got a methyl group that's right next to a CH2. All right, so with this fragment right here, we've basically taken care of 2 of our 3 signals. All right, so finally, we've got signal B. And so let's see, the chemical shift, it's around 2. Now, this is going to be fairly indicative of a motif that we'll see here at the end here. But basically, since it's around 2.0, it's an alkane that's somewhat de-shielded. All right, so it's not like this alkane. It's not just an alkane with no electronegative atom nearby. And it's not like this C, this peak right here. So we know it's not directly next to an oxygen because we would expect it to be somewhere around 4. So it's kind of in the middle, which indicates that there's something going on to account for that shifting. But we don't really have enough information to know what it is. What's the coupling? What's the splitting on this? It's just a singlet. So how many neighboring protons does it have?
2.
0, right? So it's n+1, and so if it's got 0 neighboring, it's got 0 plus 1, so we've got a signal. All right, so what do you think a signal that has 3 protons that's not next to anything, what kind of motif do you think that is? Always think simple. What's the simplest thing we have for 3 protons? Just a methyl group, a CH3, and so we don't really have any more information. We know it's likely a CH3 group, we're not sure. But typically you want to think simple before you go complex. So we know that this is a CH3 group that's going to be next to something, but it's not next to any protons. So let's think about what we've used up. All right, so we've used 3 carbons. We've used 8 hydrogens. And we've used 1 oxygen. All right, so that means left over, what we've got is going to be 1 carbon, 1 oxygen. Have we used our ring or pi bond up yet? No, so we've also got 1 unit of hydrogen deficiency. Okay, so that could be a ring or a pi bond, but it's probably not a ring, because it's going to be hard to make a ring with 2 atoms. All right, so if we've seen any structure that basically we could build from 1 carbon, 1 oxygen, and a pi bond, what's the product of, say, an ozonolysis reaction? It's a carbonyl, right? And so if we drew a structure, or at least a fragment, that looks like this, have we used up all 3 things? Sure, we have. And so now what we've got are 3 fragments. We've used up all the atoms, and we've used up our hydrogen deficiency on the pi bond right here. All right, so we've got 2 terminal pieces here on the left side, and then 1 middle piece. So there's really only one way we can put this together. We could draw a CH3 on the end, our carbonyl in the middle. We should end up with a structure like this. And so what this is pointing out here, this shift, all right, so this methyl is next to a carbonyl, and very typically, those will have shifts around 2.0 ppm. And so we saw that, well, it wasn't shifted like an alkane, it wasn't shifted like a peak down here, but it certainly was next to something different. And so what we see is that this methyl group, it was essentially de-shielded down to 2.0 next to a carbonyl, and that's going to be fairly indicative of all alkanes that are directly next to carbonyls like that. All right, so finally we need to, like most things, ask ourselves, does this make sense? So when we look at the structure that we've drawn, how many signals would we expect? Yeah, so we've got one set here, one set here, and one set here. So that's 3 different types of protons. Is that what we see in the spectrum? Yeah, and so let's see, does the de-shielding make sense? All right, so we see this is next to an oxygen, and so we've got one that's way downfield. This is not next to anything, so it's down here around 1, and then this is next to a carbonyl around 2. So that makes sense as well. And then finally, we want to think about the splitting. So we would expect this methyl to just be a singlet because it doesn't have any neighboring protons, and so we see it as a singlet. Here would we expect this? We'd expect this to be a quartet because it has 3 neighboring protons, and so that is in fact a quartet. And then finally, we have our triplet, which makes sense for this methyl group right here. So what we're going to be doing is we're going to be drawing lots of different pieces of information from our puzzle here. And so hopefully we end up with some fragments that make sense so that we can put these things together such that it matches the NMR spectrum that we've been given. Okay, this is pretty much it for today, so we'll do some examples. Okay, example number 2, C8H10O. So the first thing again, and like I said, you'll always be given the IHD formula, so all we really got to do is plug in our numbers. Here we've got 2 times 8 carbons, no nitrogens, 10 hydrogens, no halogens, plus 2, so that's 16 minus 10 is 6 plus 2 is 8 divided by 2. So what's our number? 4. So that means we've got 4 rings or pi bonds. Do we have to have 4 rings or 4 pi bonds? No, it could be 2 rings and 2 pi. It could be any combination as long as it adds up to 4. All right, so we look at our signals here. How many signals do we have? I see 5. So let's go ahead and just write those down. A, B, C, D, and E. Okay, so the integrations of these peaks, again, it doesn't show up particularly well, but you can see that the integration to this for this peak on the right is about 50% higher. And so what we've got is an integration here of 2 and 3. The integration of C looks like it matches B, so we'll just assume that's also 3. This is also 3. Finally, we should end up with, let's see. Oh, no, I was reading it wrong. So that's 3. What is C and D most likely? Does it match the peak on the left or the peak on the right? Yeah, it should be 2. So we've got 2 here, and 1 here. And we would have known that I was wrong because if we had added the numbers I initially came up with, it wouldn't have equaled our molecular formula. So these numbers, does that match our molecular formula? Yeah, we know we've got 10 protons, and so we're accounting for 10 protons, so we're good to go there. Okay, so who remembers, we talked about the anisotropic effect when it comes to chemical shifts, and so what type of structure did we see a shift down into the 7 or 8 ppm region? It was the last one we did for the anisotropic effect. And so what it is we've got 2 here and 3 here. Anytime we have a benzene type structure, that's where we have that 7 to 8 ppm. All right. And so for benzene, how many protons are there? Yeah, there's 6 protons on benzene. How many aromatic benzene-like protons do we have here? We have 5, and so what that means is most likely we've got a benzene-like structure, but one of the protons is missing, and so that's basically where the rest of the molecule is, right? That's going to be our point of connectivity for our benzene. All right, so we've got a benzene-like structure here. And so the coupling, if we blew this thing up, in a lot of cases that's what we'll do. So you'll have this spectrum, but you'll also have the boxes that are going to zoom in on this so you can see the splitting even better. If we could see this even better, what we would have is a mess. you can't always tell what the splitting patterns are. And so in those cases, what you'll typically see them referred to as are multiplets. Or in this case, we'd say the splitting is a multiplet for both A and B. And so the reason for that is we've got 5 protons, but they're splitting differently, and some of them are overlapping each other. And so you just can't see individual signals because of all this overlap. So we end up just calling this a multiplet. We know there's splitting going on, but we don't know specifically what it looks like. All right, so one thing we can assume is that our known fragment is going to be benzene-like, and it's going to have a point of connectivity off of one of its carbons. All right, so does this known fragment, is there 5 benzene-like protons? There should be, right? We've got 1, 2, 3, 4, 5 protons here, and the proton that was there, well, it's going to be some fragment that's connected to our molecule. So we've got 5 benzene-like protons. Anytime you've got 5 benzene-like protons, you're going to have a mono-substituted benzene-like case. All right, so next up, we've got peak C. So our integration is 2, and our shift is right around 3.8, which is pretty close to 4. Anytime we're around 4, what type of structure do we most likely have? Yeah, we're probably next to what? An oxygen. And so we have an oxygen in this molecule, and so that makes total sense. So our chemical shift, which is around 3.8, indicates that we're most likely next to an oxygen. Yep.
How do we know what a chemical shift is?
What was that?
How do we know what the chemical shift is?
So that 3.8, I'm just estimating, off of the x-axis. Typically, you're going to see something around, anytime you've got a peak around 4, it's most likely going to be something next to an oxygen. Yeah, but again, it's kind of like the pKa tables. We don't know specifically what the shift will be because each molecule has its own chemical shift, but what we look for is patterns. And so in this case, our pattern is we see it's around 4, so it's most likely next to an oxygen. All right, so what's the splitting on C? How many peaks do we see? It's not pretty, but I see 3 peaks, which would make it what? Yeah, that makes it a triplet. And so what this is indicating, all right, so our integration is 2. And so again, I like to start simple, and so the simplest way we could have 2 is we'd say, all right, we've got a CH2, and it's split into a triplet. So how many neighboring protons does it have? 2, right? Because of n+1 rule. So if it has 2 neighboring protons, 2 plus 1 is 3, and we expect to see 3 peaks, and that's exactly what we've got. So most likely what we're looking at is a CH2 next to a CH2. And so if it's got a CH2 on one side, well, what have we already learned that it must have on the other side? An oxygen, right? And that's based off of the chemical shift. So another fragment that we have is down here. We have an oxygen, a CH2, and a CH2. And of course, we don't have a closed shell structure on this side, so this carbon here must be connected to something else like that. So what we've got is some sort of fragment in the middle. All right, so then we get to peak D. Our integration is 2. All right, so let's see. Let's go ahead and identify. Here we've got A and B. Here we've got peak C. And if that's peak C, we need to be able to find these protons somewhere. So it's a CH2, and it has to be split somehow, right? Because it's next to these protons right here. So let's just assume it'll be a triplet. Do we have another triplet we haven't discussed? Yeah, D, right? So we've got another triplet right here, which is most likely going to be these other protons. So let's see if that makes sense. So we've got 2. We could see that it's not around 1 where we would expect an alkane, so something here on the right side must be shifting it further downfield. It's around 2.9. We can call it an alkane that is de-shielded by something. And furthermore, it is a triplet. So it is safe to say that we have located the D protons. All right, so that leaves E. All right, so what's the integration of E? Yeah, it's 1. The chemical shift is it's around 2.1 or 2.2, I guess. Doesn't give us a lot of information. More interestingly, what's the splitting of this proton? It's a singlet, but it doesn't look like any singlet we've seen thus far. How's it different? Yeah, it's fat, right? It's a fat signal. And so what this indicates is that it is a special kind of signal. So it is a singlet. But importantly, when we look at this, we can see that it is very broad, or fat, whichever one you like, I guess. All right, so anytime we have a very broad singlet like this, what it indicates is that we've got either a proton connected to an oxygen, or we've got a proton connected to a nitrogen, right? And so furthermore, these protons that are connected to an atom like an oxygen or a nitrogen, they don't even always show up. Sometimes they're just never there, right? And so part of the reason is these protons are acidic protons. The pKa of this top one, going to be 16-ish or so. And so because they're sort of acidic, they undergo exchange. And so there's actually, if it's in water, it could be undergoing a chemical change. And so sometimes it just doesn't even show up based on the environment that it's in. So we'll also say that these types of protons don't always show up. And then finally, we'll say that they rarely show any splitting pattern. Okay, so do we have an oxygen that we could connect that proton to? Yeah, so we're showing this as a fragment, but what we could say is it's just going to be this proton right here. And so interestingly enough, yeah, so this proton is connected to the oxygen, which has two neighbors, right? And so what kind of splitting would we expect for this proton? We would expect a triplet, right? Because it has two neighbors right here, but in fact what we see is a singlet. And so again, it's just these protons rarely show splitting. For the same exact reason, these protons, which we know are a triplet, well, considering that it has a neighbor right here, we might expect it to be a quartet, right? Because it really has three neighboring protons, but again, because this just rarely undergoes any splitting, it doesn't actually impact these protons at all, and we actually see a triplet. So these are just some weird characteristics about OH or NH protons in NMR spectra. They don't always show up. They're usually fat, broad singlets, and they very rarely show any splitting patterns whatsoever. All right. Have we accounted for all of our atoms? Yeah, we should have. So then let's see. Have we accounted for our hydrogen deficiency? It was supposed to be 4. Have we used up 4 units in our fragments? Yeah, so we've got 1 ring here in our benzene, and then we've got 1, 2, 3 pi bonds. And so those add up to 4. And so that tells you you can never have a benzene-like structure unless your hydrogen deficiency is at least 4, right? Just because by nature, this thing has a hydrogen deficiency of 4. So if you think you might have a benzene, that's a pretty big clue. You're going to have the deficiency. So we've got 2 pieces. They're both terminal, so pretty much we'll slap them together. And so here we saw that these protons were next to benzene. And so the shift there was a little further downfield than we expected. So it's around 2 to 3. All right, how many signals would we expect? Let's just count left to right. So this would be 1 signal. This would be a second, a third. Now over here on this benzene structure, how many equivalent sets do we have? All right, so these are going to be their own set. These would be their own set. And then finally, this one on the end would be its own set. So we would expect 6 signals. How many do we see? We see 5. So what do you think accounts for that? So over here, we just call this a multiplet, right? What's really going on over here in this benzene region is there are 3 different sets of signals, but because they're just so close together, they're just splitting into each other. And so you can't always see all of the individual peaks you would expect from benzene. But one way to basically get past that is if you ignore benzene, how many sets would we expect? 3. And so do we see the 3 non-benzene peaks? Yeah, so benzene it smudges together and it doesn't always give you the prettiest picture. So you just do your best with benzene. All right, another example. So this this one's been completed for us, or at least the hydrogen deficiency has. So we've got 5 rings or pi bonds. So again, lots of electron deficiency, and with that much, it almost, it doesn't guarantee it, but there's a pretty good likelihood that we've got some sort of benzene type structure going on. All right, so let's think about that. Do we have any signals that are stretched down into, shifted down into that 7 to 8 ppm region? Yeah, definitely we do. So we can see that signals A and B are both in that region. I mean, signal B is less than 7, but again, we're ballparking it here. It's not a perfect science sometimes. So we've got A, B, and C. All right, and so the integrations here, the computer might spit out numbers of 1, 1, and 3. But does that match our formula? It doesn't, right? Because we can see that we've got actually 10 protons in our formula, so this just adds up to 5. Fortunately, for our numbers right here, that's a multiple of 5. So really, what is the integration here? It's actually 2. This one's 2, and so C is actually 6. Now does that add up to our formula? Yeah, so now we're making sense. We always need our protons to be adding up to the total. Okay. So the integrations we've got 2, 2, and 6. And so our chemical shift again for A and B indicate a benzene type structure. But we've only got 4 protons, right? We've only got 4 benzene protons in this case. Last time we had 5, which gave us a mono-substituted benzene. But if we only got 4, is it still going to be mono-substituted? No, now it's going to be di-substituted. So we're going to have 2 different things coming off of our benzene group. And of course, because there are multiple positions on benzene, we've actually got 3 possibilities. So if our fragments are coming off of carbons that are right next to each other, we call that ortho. If they have a carbon in the middle, we call it meta, or they can be completely on opposite sides and be para. So unlike the last problem where we called it a multiplet, at least our benzene protons, in this case we're actually able to see a little better. And so just looking at it from how we can see it, what kind of splitting do we seem to see? So really I can see 2 main peaks in both cases, right? And so that's actually what we've got. So we're going to have a doublet here, and we're going to have a doublet here. So what that's telling us is that all of our benzene protons are basically split by one other proton, right? They have one neighboring proton. So between ortho, meta, and para, which one makes sense for that? You can rule out meta because how many sets of protons does the meta substitution have? It's got 1 here, 2 here, and 1 here. So 3 different types of protons. So we know we only see 2 signals here, so it can't be meta because we would expect 3 peaks. Let's think about a proton right here, all right? So this ortho proton right here, let's say that it's got a neighbor here and a neighbor here. And so what kind of splitting would we expect? If it's got 2 neighbors, we'd expect a triplet. Do we see a triplet anywhere? We don't. All right, so let's go to para. We would expect these 2 to be equivalent and these 2 to be equivalent. What would the splitting be expected to be here? Doublet. What about here? It'd also be a doublet. And so what we find is that in the para substitution, we expect to see 2 signals and both of those signals to be a doublet. So by thinking about our benzene information in these good cases where I guess we can see the splitting clearly in our benzene, we're able to determine what kind of substitution we've got here, be it ortho, meta, or para. All right, so we've got 2 doublets, and so that indicates that we've got our para substitution here. So when we draw our fragment, that tells us we're going to have something coming off the top and something coming off the bottom, but we don't know what it is. All right, so that leaves us with signal C. All right, so this one's interesting. The shifting is around 4.0, which indicates what? Yeah, so if we're around 4.0, it indicates that we are next to an oxygen. What's the splitting? Just throw a guess out there. Yeah, it looks like a doublet, right? All right, so we've got a doublet there. Let's think about if that makes sense. All right, so we've got 6 total protons. Can we stick 6 protons on 1 carbon? No, so what we're going to have to do is have most likely equivalent sets of methyls, right? If we had one CH3 and another CH3 that were the same, that would add up to 6. So let's think about what this could look like. The only thing I could come up with would be, let's say we have CH3, CH3. And so if they're split into doublets, we're going to have 1 proton off the neighboring carbon, and then there's some other stuff going on. All right, so this does make sense. This would integrate to 6. And so furthermore, we would expect it to be a doublet. But what are we kind of overlooking in this case? Do we have any more signals? We don't. All right, so we're drawing a structure. These have to be split by a proton here, but we're not seeing a signal for this proton. What kind of splitting would we expect for that proton? N+1 rule. We would expect a septet, right? And so if this were the true nature of these peaks, we would expect that somewhere on our somewhere on our spectrum, we would find that this proton's showing up, and it would be showing up as a septet, but we don't see that. There's nothing else to the right here. I'm not hiding anything from you. This is all we've got. So could this possibly be the correct structure? No, it can't be right. What we could have, and in a case like this, what can happen is, and instead of thinking about this as peak C, let's think about it as peak C and peak D. And instead of having 1 doublet, let's think about these things as singlets. So let's say this integrates to 3, and this integrates to 3. And so instead of a doublet, let's just call them a singlet and a singlet. Now they're still both next to an oxygen, right? They're both shifted down to about 4.0. So if we thought about what this could be, all right, they're singlets. Do they have any neighboring hydrogens? They don't. And so what we could have is, let's say one of these will be an OCH3. And the other one, there's not a lot to work with here, so let's again call it an OCH3. Now, if these were just 2 OCH3s and there was symmetry in the molecule, we would expect the same chemical shift. But do these 2 peaks have the same chemical shift? No, they don't overlap. We see 2 discrete peaks, and so what that tells us is that these 2 things are definitely inequivalent. So somehow when we draw a final structure, these things can't be such that they are equivalent protons. All right, so what have we used? We've used 6, 7, 8 carbons, so that's C8. We've used 4, 7, 10 hydrogens, and we've used 2 oxygens, so that leaves 1 carbon, 1 oxygen. And what about our hydrogen deficiency? Yeah, so how many have we used up to this point? We've used 4, right? We've got a ring here, and then we've got 3 pi bonds here, so that's a total of 4, but we know that our structure, based off of our formula, must have 5. And so we've got 1 unit of H deficiency. So what kind of structure? We've seen this once already. What is that most likely? Yeah, it's a carbonyl, so we can account for that with a carbonyl that looks like that. All right, so now we've used up everything. We've got 2 terminal fragments and 2 middle fragments. And I really think there's only going to be one way to put this together. So if we draw our benzene, we'll just put an OCH3 there. And then we'll put our carbonyl between our OCH3 there. All right, so are these 2 methyl groups, would we expect them to be equivalent? Now they definitely have different connectivity, right? So we would expect different signals. So this is just, I guess, an example of how it's not always totally clear. You can't just point to something and assume that it's going to be a doublet. You have to keep putting the information together and dig a little deeper to make sure that these things make sense. How many signals would we expect for this structure? So we've got the 2 methyls, that's 1 and 2, and then how many sets of equivalent protons on the benzene? Yeah, we'd expect 2, right? So these have the same connectivity, and these have the same connectivity. So we expect 4 different sets. Do we see 4 peaks? Yeah, that makes sense. We've got a CH3 here and a CH3 here. We would expect to be a singlet around 4. And so we see our 2 singlets around 4 here, and then down here we see our benzene peaks that have been shifted down. Okay, where are we at on time? 11:39. All right. So let's talk about, I don't think we'll have time for another example. So let's talk about carbon NMR for a few minutes. And so I said that proton NMR is by far the most commonly used NMR. And so that's why, or the reason for that is carbon-12 is NMR active. It is not, but carbon-13 is NMR active. So fortunately for us, we find that any given sample of carbon is going to be about 1% carbon-13. So what that means is you're going to have, say, 100 molecules. And if you try to do carbon NMR, you're not going to see 99% of them, right? Or I guess 99 of them. The only one that you'll see is that one that has a carbon-13 in there. And so for that reason, we can only see about 1% of the carbons, and so the signal is much weaker. Your time scale of your experiments for a proton NMR, it'll take you 30 seconds to get a clean one. For carbon, it can take an hour sometimes just because the signal is so faint. You can see that it's really, really, really faint compared to the proton. All right, so let's think about splitting. So we have a 1% chance of a carbon-13 being in location A and a 1% chance of a carbon-13 being in location B. What's the likelihood of having 2 carbon-13s actually next to each other? It's 1% of 1%, right? It's very, very unlikely. And so for that reason, we don't really end up seeing any splitting between 2 carbon-13 nuclei, right? It's because it's just very, very unlikely for 2 carbon-13 nuclei to be next to each other. So there's no splitting there. What you can see splitting in is basically between a carbon-13 nucleus and a proton nucleus. And in fact, that makes these things really, really, really messy. And we don't like messy because it's hard to figure. So what you do is you do a special type of experiment that basically decouples the carbon-13 from the proton. So while the protons could be splitting the carbon-13 nucleus, we just wipe it out. We basically pulse them with some radiation such that they're undergoing rapid transition, and so the carbons only see one spin state for the proton. So again, we keep these as just singlets, and so this is pretty representative of what a carbon-13 spectrum will look like. It's just singlets. You can see that the scale down here is a little different, and so for carbons, I guess it's written that you would expect signals between 0 and about 220 ppm. For proton, you're usually shown about 0 to 10 ppm. All right, so it's not really complex. All it is that it's just broadened, right? We see the same chemical phenomena. So when we have carbons that are next to electronegative atoms and de-shielded, we end up seeing those downfield. Now, we've just seen examples where protons that are de-shielded by oxygens, where do they come in around in ppm? It's around 4, right? And so for a carbon, it's just further downfield. In this case, it might be more like 130 or 140. But again, it's the same exact idea. So what we can do is you'll have tables like this. And these are very similar to pKa tables in that they're not specific numbers, right? Because there's lots of different molecules, lots of different variety both in their structure as well as the resulting shifts that we see. And so if you're given something like this basically gives you an idea of where we expect to see certain motifs of certain structures based on their chemical shifts. But of course it's ranges because we can't know specifically what they are. All right, so let's just do a comparison between proton and carbon. So we know that a proton is just a regular alkane. You can see they're listing 0.5 to 3. I think I gave you like 0.8 to 1.7. Again, there's not discrete cutoffs. There's always going to be cases that might be a little further than you expect. For the, let's see, so this is an alkane. And so the corresponding carbon shift for a typical alkane is right here, and you can see it's about 0 to 40. So they're both going to be very shielded because there's nothing around them to de-shield them. And so if we keep going, we can find that, say, an alkyne, which we've learned is around 2.5 or 3. So that's a little downshifted for a proton, and so we expect the same thing, and that's exactly what we've got. So what we see is an alkyne, and the carbon is downfilled, and so it's about 65 to 85. Our alkene peaks are, for the protons, are shifted to around 5.6. And so we would expect the carbon to be even further downfilled than the alkyne, and that's exactly what we see. So here you can see that we've got 100 to 150 for the alkenes. Again, it's just further downfilled. We're just changing the scale, but the idea behind the scale is the same exact thing. Let's see. All right, so we've got a carbon next to an oxygen. So we can see that those shift up here anywhere between like 160 or 210 when they're part of a carbonyl like that. So that's going to be very characteristic. Finally, we see aromatic peaks in the protons. We're just about the most that we've seen in practice. And so here we've got our benzene-like stuff. And so it's the same thing for carbons. We see our benzene-like stuff is pretty far downfilled. But so, yeah. Very similar trends in terms of the shifting. Notice that the carbons, so alkenes are about 1 to 150. Benzene type are 110 to 160. So it's not always clear. It's not always the easiest thing to distinguish. And that's why proton NMR is used a lot more, because we get a lot more info from it. But there are cases where carbon NMR can be really useful, basically as a supplement to the proton spectra. And so typically you'll be given both as information. All right, so it is 11:45. So let's talk about exams for a minute. So the average was up on this one. Exam 1 average was a 139. Exam 2 average was a 145. What really jumped up was the median. So the median on exam 1 was around a 140. The median on this one was about 151. So the average is like 6 points below the median. So while a lot of people really did well on this one, there were also a few where the scores are really pulling down that average quite a bit. Score breakdown, there were more A's than C's. I think between the two sections, we had like 95 A's. Honestly, as a group, you did really well on the exam. I'm very sorry to say that while you had the higher average on exam 1, 10 o'clock had it on this one. So there's about half a point difference. And then let's see. Yeah, I said this in an email, and I'll say this throughout the semester. If you've got concerns about your score, you know, the point of this, I don't care how much organic chemistry you really know in February, because the point of this is not, you know, for me to come away grading you based on that. I really want to know how much organic chemistry you know on May 4th, right? Or at least by May 4th at the end of the semester. So if you've got scores that you're unhappy with, I don't care what those are, as long as if by the end of the semester you've shown me that you have learned organic chemistry. I will give you a grade that is indicative of what you know about organic chemistry, and so you have that opportunity throughout the rest of the semester. So I'll say this, I mean really, I don't care if you failed both exams. If you come back and get an A on the final, that tells me that that's your level of understanding of organic chemistry, and so I will grade you accordingly. So don't feel like you've got a couple of bad exam scores and your semester is toast. It's really not. You've got a lot of points left to be earned. If you want to talk about grades, don't hesitate to email me, and we can try to talk about study strategies and a plan going forward. All right, so we've got A to G over here. Any questions? Okay, A to G here. We've got H to, what comes before P? O, H to O. And then over here we've got P to the Let me just briefly add, I had a couple of graders helping me out on this exam. If you've got concerns that maybe your exam wasn't scored correctly, just let me know and we'll look at it. Also, check on Blackboard and make sure that your score corresponds with what's on your exam. Help keep me accountable.
I'm supposed to be with you at 12. Should I wait at your office and avoid this craziness?
Yeah, actually, just take a seat.
All right,
we'll,
cool.
We'll talk once.
All right, awesome.
Yeah.
you doing? Really? I was really ashamed because usually the R's are over there, but now the R's are over here. Little. Yeah. Oh, thank you.
I got you.